which is solution of linear programming problem. And last time we have discussed big M method. Now we are going to discuss two-phase method for solving the linear programming problem. So what are the artificial variable? I am repeating again. The slack and surplus variable are used to convert the linear programming problem into the standard form. But when we go for obtaining initial basic feasible solution, then in case of surplus variable, it is not possible to obtain identity matrix for obtaining the initial basic feasible solution. That is in the situation where constraint contain greater than equal to sign or equal to sign, it is not possible to obtain identity matrix. So for obtaining the identity matrix, artificial variables are introduced into the linear programming problem with constraint coefficient +1. The cost coefficient of these variables depends upon the method used. And these variables are also non-negatively restricted variables. These are used when constraint contain either greater than equal to sign or it contain equal to sign. The techniques which deals with artificial variables are called as artificial variable techniques. There are basically two techniques. One is called as big M method or Charney's method. Other is two-phase method. The two-phase method is called as two-phase method because the problem is solved into two different phases. That's why it is called as two-phase method. In first phase, before going to first phase, something has to be done, which is step 1 called as identify and formulate the problem. And standard step 2 is convert the linear programming problem into the standard form using slack, surplus and artificial variables. But this conversion is for only constraints, not for objective function. That means constraints are converted into the standard form using slack, surplus and artificial variables, and then obtain the initial basic feasible solution. Now, after obtaining the initial basic feasible solution, the first phase of this method is started. And in first phase, we take the objective function as negative sum of the artificial variables. That means if we have L variables, then we can write objective function as maximum of Z is equals to minus A1 minus A2 so on minus AL. That means negative sum, or you can write minus within bracket A1 plus A2 plus so on AL. Then in next step, the LPP is solved in same manner as in simplex method. That means construction of simplex table, then obtaining of net evaluations Zj minus Cj, then select the most negative net evaluation if at least one is non-negative, if at least one is non-positive, then obtain the most negative net evaluation and then calculate the ratio and select the minimum ratio. The variable corresponding to most negative net evaluation will leave the basis, and the row variable corresponding to minimum ratio, the variable corresponding to most negative net evaluation will enter to the basis, and the variable then construct new iteration by making leading element as 1 and all the other elements for the column of entering variable as 0. In the end, the process is repeated until all net evaluations become non-negative. In this situation, If all the net evaluations become non-negative, then we can obtain one of three conditions. First condition, that all and in the situation, in first condition we obtain that all net evaluations are non-negative and no artificial variable occur in the optimum basis, which means that our solution is optimum. That means in XB there is no artificial variable, or you can say there is no AI, then we said that our solution is optimum. The second condition is that all the net evaluations are non-negative and at least one of the artificial variable occur in the optimum basis with zero value. That means in XB there will be an AI which have value 0, at least one AI which have value 0, and all the net evaluations are non-negative. In this case, the solution is said to be degenerate. And for moving to next phase, it is required to remove the degeneracy. Whereas it is not a scope of the today's lecture to how to remove the degeneracy. In third condition, all net we obtain that all net evaluations are non-negative and at least one artificial variable occur in the basis with some positive value. That means all Zj minus Cj are more than 0, sorry, are greater than 0, and at least one AI have some value. That means it may be 2, it may be 200 or 2000, any value, then solution is said to be infeasible. Now, when we obtain the optimum solution in phase 1, that means all net evaluations are non-negative and no artificial variable occurs in the optimum basis, then we move to phase 2. In phase 2, the original objective function is considered as in standard form. That means if the original objective function is minimization type, then it is converted into the maximization type. And the optimum solution of phase 1 is taken as the initial basic feasible solution for the phase 2. That means you can say in a very simple manner that the last iteration or final iteration of phase 1 is taken as initial iteration for phase 2, but the two changes are to be done. One, the artificial variables must be removed from the table, and second, the original cost coefficients should be placed in the iteration. So how, and then it is solved in the same manner as simplex method, and after solving in same manner as simplex method, we will get optimum solution. For explaining two-phase method, I am going to solve this example, according to which the objective function is minimization of z, which is equals to x1 plus x2 plus x3. Subject to constraint x1 minus 3x2 plus 4x3 equals to 5. Second constraint is x1 minus 2x2 less than equals to 3. And third constraint is 2x1 plus x3 greater than equals to 4. And variable x1, x2 are restricted, whereas x3 is unrestricted. So for converting into standard form, we can replace x3 as it is unrestricted by the difference of two new variables x3 dash and x3 double dash. That is, I have taken x3 is equals to x3 dash minus x3 double dash and put in it into the constraints as well as objective function. Objective function is transformed using min-max theorem, that is minus of minimum of minus z is equals to maximum of z. Using it, we obtain the objective function as maximum of z1 is equals to minus x1 minus x2 minus x3 dash plus x3 double dash. First constraint contain only equal to sign, therefore artificial variable is used only, no slack or surplus variable is used, and constraint will become x1 minus 3x2 plus 4x3 dash minus 4x3 double dash plus a1 equals to 5. Second constraint contain less than equal to sign, therefore it is in it slack variable is introduced, surplus and artificial variables are not used in this constraint, and constraint would become x1 minus 2x2 plus s1 is equals to 3. And third constraint contain greater than equals to sign, therefore a surplus variable as well as artificial variable is introduced in this constraint, and the constraint would become 2x2 plus x3 dash minus x3 double dash minus s2 plus a2 equals to 4. And all the decision variables, slack variables and artificial variable and surplus variables are non-negatively restricted. Now it is converted into the into the matrix form, and the constraint would be obtained as this. It is the constraint coefficient matrix, it is your decision variables matrix, and it is constant matrix. Now we take the initial matrix as identity matrix. So B is equals to 1 0 0 0 1 0 and 1 0 0. So here you can see that first column is this one, that is the seventh column of the constraint coefficient matrix, and associated variable will be a1. So taking xb is equals to s1 a1 a2 and b is equals to 5 3 4, we would obtain that s1 is equals to 5, a1 is equals to 3 and a2 is equals to 4. Now as we have used 2 and problem is moved into the phase 1 after obtaining initial basic feasible solution. Now as we have considered two artificial variables a1 and a2 into the standard form, therefore for phase 1 we write the objective function as maximum of z2 is equals to minus of a1 minus of a2. And we will not consider any objective function which was given in the problem, only the negative sum of the artificial variables. Now simplex table is constructed, and after constructing simplex table, net evaluations would be obtained. So here you can see the in CB the cost of artificial variables are written as well as slack variable is written. So the net evaluation will be minus 1 into 1 plus 0 into 1 plus minus 1 into 0. That will give minus 1. Similarly for x2 it would be obtained as plus 1. For x3 it will be minus 5. For x3 double dash it will be plus 5. For s1 it will be 0. For s2 net evaluation will be 1. For a1 net evaluation will be 0 and for a2 net evaluation will be 0. That means all the net evaluations for the variables in the basis, that is a1, s1 and a2 net evaluations are 0, whereas some other net evaluations are either positive or negative. Since there is a negative net evaluation minus 1 and minus 5, we will select most negative, which is minus 5. It's according to it, the corresponding column variable x3 dash will enter to the basis. Now we calculate the ratio xbi upon xir such that xir greater than 0. That means divide the value in xb by the corresponding element in the column of entering variable. First will become 5 upon 4, that will give 1.25. Second is 0, therefore ratio is not calculated, as we have written the condition xir should be greater than 0. It is equal to 0, it is not greater than 0, therefore ratio is not calculated. And third ratio is 4 upon 1, that is 4. Now among 1.25 and 4, the minimum value is 1.25. Therefore corresponding row variable a1 will leave the basis. So x3 a1 will be replaced by x3 dash, and the leading element will become 4. So making leading element as 1, we divide the constraint by 4. Sorry, row 1 will be divided by 4, and for making other element as 0, second row will remain as it is, and for third row it is new first row will be subtracted from it. That is, our transformation will be r1 prime is equals to r1 prime is replaced r1 upon 4, r2 prime is written same as r2, and r3 prime will be written as r3 minus r1 prime. So the coefficient in the column of x3 will be changes 1 0 0, and corresponding row operation will be performed from the column of xb to the last column, that is up to a2. And cost of x3 was 0, so it is also 0. Again net evaluations are calculated. Here you can see that one net evaluation for x2 is minus 11 upon 4. Therefore we can say that x2 will enter to the basis, and all the other net evaluations are positive, therefore we will not consider it. Now we calculate the ratio xpi upon xir such that xir is greater than 0. First value in x2 is negative and second value in x2 is negative, therefore these ratios are not calculated. Only one ratio is calculated. A value of a2, that is 11 upon 4, will be divided by the coefficient in the third row of x2, that is 11 upon 4. It will give 1. Since there is only one value in the ratio, it is considered as minimum, and corresponding row variable a2 will leave the basis. Now our leading element will be 11 upon 4, as the line of a2 and x2 intersect at 11 upon 4. Now this 11 upon 4 will be converted to 1, and other two elements minus 2 and minus 3 upon 4 will be converted into 0 using elementary row operations. So on applying these elementary row operations, we would obtain this table, which is our iteration 2. That it will give value of x3 equals to 2 and value of x2 is equals to 1, and slack variable s1 is equals to 5. And then we calculate net evaluations, and we can see that all net evaluations are either 0 or positive. So we can say that there are all the net evaluations are non-negative, and no artificial variable occurs in the optimum basis. Therefore, it is an optimum solution for the phase 1, and problem will be moved to phase 2. Now in phase 2, we consider the original objective function in the maximization form. We have converted our original objective function was minimization type, and we converted it into the maximization type. So it will become maximum of z1 is equals to minus of x1 minus of x2 minus of x3 prime plus x3 double prime plus 0 s1 plus 0 s2. As artificial variables are removed from the basis, therefore we remove here the column of artificial variable. There is no column of artificial variable in phase 2. And in CJ, if you see on previous table, here the cost of x1 x2 x3 prime and x3 double prime was 0. Now we put here original cost, that is minus 1 for x1 minus 1 for x2 minus 1 for x3 prime and 1 for x3 double prime. In same manner, costs in cost of basic variables are also changed. For x3 it will become -1, and for x2 it will also -1, and for s1 it will remain 0. Now this part of matrix will be same as the previous matrix. Here you can see 2 by 11, 9 by 11 and -1 by 11 in x1. So in phase 2 it will also same 2 by 11, 9 by 11 and -1 by 11. For x2 it was 0, 0, 1. Here you can see it was 0, 0, 1. For x3 it is 1, 1, 0. Here you can see x3 prime it is 1, 1, 0. For x3 double prime it is -1, 0, 0. So here for x3 double prime it is also -1, 0, 0. For s1 it is 0, 1, 0. And for s2 it is -3 by 11, -8 by 11 and -4 by 11. So for s2 here it is -3 by 11, -8 by 11 and -4 by 11. That is, the optimum solution of phase 1 is taken as the initial solution for phase 2, as well as the constraint coefficients in the last iteration was taken in same manner. Now we calculate net evaluations. So for x1 net evaluation is obtained as 10 by 11. For x2 it is 1. For x3 it is 0. For x3 double prime it is 0. For s1 it is 0. And for s2 it is 7 by 11. That means we can obtain that all the net evaluations are non-negative. So this table provides us the optimum solution of the given problem. So we can say the solution of given problem is x1 is equals to 0, x2 is equals to 1 and x3 is equals to 2. Now we put it into the objective function in minimization type, which was our original objective function, that is minimum of z is equals to x1 plus x2 plus x3. Then we would obtain that the minimum value of objective function is 3. So it is the end of today's lecture.